Hello and welcome back to another EE140 video. Today we'll be solving a plane waves problem from midterm 2, fall 2019, question 3. So our problem states that the magnetic field of a 1592 MHz plane wave propagating in a non-magnetic medium is given by this H field. Now we want to go ahead and find the corresponding expression for the electric field. So we'll be using what is called a three-step method. So the first property of this three-step method states that the E field and the H field are always in phase. And this is true because if we look at our E field and our H field as a function of position and time, we can see that our E field's propagation is the same as our H field's propagation. So since the E field and the H field are in the same phase, we can go ahead and write that our E field is equals to E naught times the same phase that was given to us in our H field. So this 10 to the power of 10 came from omega equaling 2 pi f. And since in our problem statement we're given f as 1592 megahertz, we just go ahead and plug that in. So 2 pi times 1592 times 10 to the 6, because it's in megahertz, gives us a value of 10 to the power of 10. So now if we go ahead and look back at our E field and our H field, we can see that our E field is in the X direction, our H field is in the Y direction, and our propagation is in the Z direction. So X, Y, Z brings us back to our right-hand rule, which gives us the second property of this three-step method that states K is equals to E cross H. And also E is perpendicular to H, which is also perpendicular to K. So now we'll go ahead and draw our H and K direction in order to find our E field's direction. So we can see that our H field is in the Y direction and our propagation is in the X and Z direction. So when we create our graph, this is basically an arbitrary graph. So you can choose what to label your axes to help you understand and visualize the directions of each field. So I'm going to label my axes X and Z because I know my propagation is in those directions. So when we pull out K, K is going to be equals to negative 40x plus 30z. Now you may be wondering why our propagation here has the opposite signs as our propagation here. And this is due to the equation of cosine or sine omega t minus k dot r. So pretty much since we have this minus sign, this basically tells us that we have to flip whatever is given to us. So our propagation is in a positive 40x minus 30z direction. So when we pull out our propagation, we'll have it in the negative 40x plus 30z direction. So if we go ahead and draw our K, it will look something like this, negative 4 and 3. So if we remember a three-dimensional axis is labeled such as X, Y, and Z. So if we relate this graph to our original graph, we can see that our Y direction is going into the page. And since our H field is in the positive Y direction, we can say that our H field is also going into the page. So if we remember the right-hand rule, our thumb is our K, our index finger is our E, and our middle finger is our H. So if we take our thumb and point it in the K direction, and we take our middle finger and point it going into the page, we will have our index finger as in the first quadrant. So our E field will be labeled as 3, 4, and this is because the angle here needs to be at 90 degrees. Since we also know that this angle is equal to this angle, so the tangent of this angle has a 3:4 ratio, meaning that this angle's tangent also needs to have a 3:4 ratio as well. So since we know E, we can write the E field's direction as E is equals to 3x plus 4z over 5. And we divide by 5 because we only want the direction, not the magnitude. So in order to make this a unit vector, we need to go ahead and divide by the magnitude. And we found the magnitude to be 5 by taking the square root of 3 squared plus 4 squared, which gave us 5. Now, since this problem doesn't state that we're in air vacuum, we need to go ahead and find our index of refraction. So the first step to finding our index of refraction, we can say that the wave speed is equals to omega over the magnitude of our k. So we saw that omega was 10 to the 10 earlier, and the magnitude of our k will be 50. So 10 to the power of 10 divided by 50 will give us a value of 2 times 10 to the 8. Now we can relate our wave speed to our index of refraction by saying the wave speed is equals to c over n. And since we want our index of refraction, we can rewrite this equation as n is equals to c over v. And in this case, c is our speed of light constant, which is 3 times 10 to the 8. And we just found v to be 2 times 10 to the 8. So that gives us an index of refraction of 1.5. And the index of refraction basically tells us how much light would bend when it comes to a certain medium. So for the final property of this 3-step method, it states that the magnitude of this wave, the ratio of E over H, is equal to eta, which is our wave impedance. So since we want to go ahead and find our electric field, we can rewrite this equation as E naught is equals to eta times H naught. And in order to find eta, we can say eta is equals to eta naught divided by n, which is our index of refraction. Now, eta naught in a vacuum or air will always have an impedance of 377. And this is because the impedance in an air or vacuum is defined by the permittivity of space, mu naught, divided by our magnetic constant, epsilon naught. So we know mu naught has a constant value of 4 pi times 10 to the negative 7, and epsilon naught's constant is 8.85 times 10 to the negative 12. Now if we go ahead and take the square root of that, we get 377. So now that we know how eta naught is found, we need to go ahead and divide that by our index of refraction, which we found to be 1.5 earlier. So 377 divided by 1.5 gives us a wave impedance of 251. So now if we go ahead and look back at this equation, we can say that E naught is equals to 251 times H naught. And if we go ahead and go back to our problem statement, we can see that H naught has a value of 10, but 10 is in milliamps. So 10 milliamps is equivalent to 0.01. So 251 times 0.01 gives us a value of 2.51. So now that we have our direction, magnitude, and phase, we can go ahead and write our final equation to be that our electric field is equals to the direction, which we found to be 3x plus 4z over 5 times the magnitude, which was 2.51, times our phase, which was sine of 10 to the power of 10t plus 40x minus 30z plus 0.1 pi. And the units are going to be volts per meter. Now we can go ahead and simplify this one more step to where our electric field will be 1.5 in the x direction plus 2 in the z direction times our phase, which was sine 10 to the power of 10 t plus 40x minus 30z plus 0.1 pi. And once again, our units are volts per meter. And that is our final answer for our electric field.